Welcome to this session. This session will state and prove the second property of Jacobians. So we say that if U, V are functions of R and S, and R and S are also functions of X and Y, then the Jacobian of U, V with respect to X, Y is the same as the product of Jacobian of U with respect to RS and Jacobian of RS with respect to XY. So we are interested in proving this relation. So proof. So we know that the Jacobian of UV with respect to RS is given by the determinant partial U, partial R, partial U, partial S, partial U, partial V, partial R, partial V, partial S, and Jacobian of RS with respect to XY is the determinant of partial R, partial X, partial R, partial Y, partial S, partial X, partial S, partial Y. This by definition. So which means if I say partial U, V, partial R, S by partial R, S, partial XY, I get the determinant partial U, partial R, partial U, partial S, partial V, partial R, partial V, partial S. I multiply by the determinant partial R, partial X, partial R, partial Y, partial S, partial X, partial S, partial Y. So let me call this question 1. Now, transposing the second determinant in 1, we get, so remember, transpose of a matrix doesn't affect its determinant, so the sign will remain the same. Partial UV, partial RS, and then times partial RS, partial XY will be determinant partial U, partial R, partial U, partial S, partial V, partial R, partial V, partial S, and then times. Now here we'll have partial R, partial X, and then partial R, partial Y, and this will be partial S, partial X, partial S, partial Y. So this is the determinant of this, the transpose of that determinant. Now let's evaluate this determinant, the product of these two determinants. So Remember, when you're multiplying two determinants, it is row by row, not row by column. So this will be have this row and this row. So partial u partial r times partial r partial x plus partial u partial s times partial s partial x. So this is the first element. Then an element here will be this row times this row, partial u partial r times partial r partial y plus this element and this element, partial u partial s times partial s partial y. And then here will be this row times this row. So partial v partial r times partial r partial x plus this by this. So partial v partial s times partial s partial x. Here we have this row and this row, partial v partial r times partial r partial y plus partial v partial s times partial s partial y. And remember, have this expression here. So this is the product. But partial u partial r partial r partial x plus partial u partial s partial s partial x is here the definition of partial u partial x. This by chain rule. Like this and these are canceling, this and these are canceling. So partial u partial x. And then next one, this one here, partial u partial r partial u partial r so partial u partial r times partial r partial y plus partial u partial s partial s partial y is, so remember this is u. It's like we close this and this, close this and this one just defines partial u partial y. Because like this and this process of uy. And then partial v partial r partial x plus partial v partial s partial s partial x. This and this and this is a chain rule for definition of partial v partial x. And lastly, partial v partial r partial y plus partial v partial s partial y is the definition of partial v partial y. Because this and this and this one, this is just definition of partial derivatives by chain rule. Now, if I had called, or if I call this, all this, if I call them 2, then replacing 2 in 1 will have this position will be replaced by partial u partial x, as we have seen here. This will be replaced by partial u partial y. This will be replaced by partial v partial y. This will be replaced by partial v partial x. So this is U. So therefore, that product so this implies that partial U V partial R S times partial R S partial X Y is the same as the determinant. So we have partial U partial X and we have partial U partial Y. And this one is partial V partial X. And this one is partial V partial Y. And you see, this is nothing but definition of the Jacobian of U V with respect to X, Y. So that's how we prove that. So similarly, if we have Jacobian of U V W with respect to X, Y, Z is the same as Jacobian of U V W with respect to R S T multiplied by Jacobian of R S T with respect to X, Y, Z. You can as well prove this one just as we have done in that case of two variables, U, V. Thank you.